Good morning and welcome everybody to this 14th edition of the Castiel Code of the Month. Today we can showcase work from the ESiWACE3 COE, and we have our guest is today Juniper Tyree from the University of Helsinki. He will present their work on the online compression laboratory for climate science and meteorology, so dealing with lossy compression of this vast amount of climate meteorology data. So Juniper, I'm happy to have you here, and the floor is yours.
Oh, thank you very much for having me today. So yes, I am Juniper Tyree. My pronouns are they, she. I'm a PhD student at the University of Helsinki, and inside of ESiWACE3 in work package 3.2, I'm leading the effort on exploring data compression, lossy data compression in particular, on data that comes from weather and climate models. And what I will talk about today is our work on building an online laboratory for compression, but also more generally for climate science and meteorology, and how that allows you to explore, for instance, data compression just from the comfort of your web browser. And of course, this is not just my work alone, but I work as part of a bigger team inside of ESiWACE. And in particular, Sarah, Peter, Carsten, and Heikki have all contributed to this work. Perhaps to start, I will again give a bit of a scope of where this project fits in. So in ESiWACE, we're of course concerned with supporting the entire European community on weather and climate modeling. And inside ESiWACE, we have work package 3, which is all about tackling the challenge of the amounts of data volumes we're now having to deal with. And inside of that is domain-specific data compression, the part which I'm working on. So what I'm going to talk about today is starting a bit with sort of motivation. Why do we at all need to use lossy compression, and sort of what's our problem with it at the moment? Then I'm going to introduce a bit what we call the compression laboratory, which are essentially some experiments, some showcases of compression that you can apply. And from that, I will then build on sort of the bigger project, which is this open science online laboratory for climate and meteorology. And then I'll give some future outlook on things we're working on at the moment and collaborations we are pursuing, and where this is all heading back to our motivation from compression. But let's perhaps start with lossy compression as our sort of original use case. The problem is, of course, that the amount of data size has just been growing exponentially. Here you can see a plot just from the ESMWF archive size. It's a log-log plot or lin-log plot. So you can see as time has linearly grown, the amount of data has grown exponentially. And there is no really an end in sight. We just keep on producing more detailed climate models with higher resolution, more ensemble members. So clearly the amount of data is going to keep growing, but at the same time, we're not really keeping up with the costs. Of course, there's just the cost of the data itself. You need to store it, you need to archive it. Every time somebody wants to analyze the data, you need to first transfer it over the network. They need to store it. There is an I/O cost, and then operating anything over that data. So at every step of the way, this data is costing us more and more, and the amount of data storage, the amount of processing, the speed with which we can process things is just not keeping up. So in order to avoid a point where we would need to restrict the amount of data we can produce, and thereby restrict the science we can do with it, we need to make sure that we can sort of get the same quality with just less, and with a lower volume of data, and that's where compression comes in. Of course, one might think that the problem is already solved because there have been, on the compression side, quite a few papers on various approaches for lossless and lossy compression that promise really good compression ratios. So on the left here, we have the bit information paper by Milan Clover. On the right, we have a semi-implicit neural compressor, and both of those offer compression ratios in the sort of like factor of tens, hundreds, or even with the neural compression factor of thousands. So are we just done here? Can we go home and just apply this compression? Well, there's where the sort of problem comes in, which is that lossy compression is really scary, and especially when you're doing domain science. So one way the conversation at the moment still often goes is we have from the computer science, from the information science side, some really great new compression algorithm that comes with some information loss that promises a lot. And then, of course, once we start talking with domain scientists, it's like, great, I want less data. but actually there's a whole list of requirements that I have that are never written down anywhere, but I'm scared that any of them will not be fulfilled by the lossy compression anymore. And so maybe let's rather not use lossy compression. Let's stick to either no compression or just lossless compression. And so we have this really big gap between what the possibility is and what we are actually using at the moment. And we need something to fill that gap. And that's where our work package is coming in. We want to sort of bridge the gap between the lossy compression algorithm and the promise they have and the requirements from the domain weather and climate science side, and sort of find a nice matchup so we can use them together. And to sort of sum that up a bit, the problem really is we need lossy compression. There are methods for it, but we're avoiding to use it. One issue is that those requirements that would allow us to use lossy compression safely are just not specified anywhere in clear terms. So they're very vague, domain-specific, problem-specific, and without clearly defining them, of course, we also can't know what methods we can use that might satisfy them. And then the big one is that there's just a lack of trust in lossy compression. Information loss sounds scary. If you don't know what your safety requirements are, it's very hard to argue that you're fulfilling them. And especially, we want lossy compression to be applied by, of course, everyone, everyday domain scientists, and they don't have the time to investigate different compression methods and really learn about their trade-offs. So we need a solution that is easy to use, that can be trusted, and where you don't have to think about, is this safe to use or not? And this is where our idea of fearless lossy compression comes in, and sort of the roadmap we have to there. The first really important step is we need to really establish what are our safety requirements. So if we apply lossy compression, what amount of data can we afford to lose? For instance, because there is already noise or uncertainty in the data, and we don't need to store sort of a particular manifestation of that. But of course, we also want to make sure that we don't lose anything important. So specifying exactly what those requirements are is a critical step in then making sure we can actually meet them. And the second part is the trust building. How can we build trust in lossy compression? And importantly, how can we simplify this? And some parts that we're working on is, one, combined with the safety requirements, is benchmarking the popular existing compressors. Both, of course, for performance, we want to have a method that gives you lots of compression and runs well and fast. But of course, really importantly, to trust it, we need to make sure it's safe to use. So finding out which compressors meet our existing requirements and which don't. The second part, and sort of a bit adjoined to it, is providing safeguards. So finding a way to make any existing compressor safe to use, even if the underlying compressor doesn't itself provide those guarantees, finding a way to sort of wrap it up nicely. So again, a domain scientist can just use any lossy compressor, and we make sure that actually no important information is lost. And then finally, and this is the part that sort of binds everything together, and I will mostly focus on today, is if we want to build trust in lossy compression, the only way we see as that being done is by allowing scientists to convince themselves that it's safe to use. And a big important part of that is trying things out yourself. And that's why we've been developing this online compression laboratory. And that's where we move to next, this compression laboratory. A very simple way to think about it is, it's a combination, a collection of notebooks, Jupyter notebooks, examples that showcase how you can compress data, what the effects of that data compression are, and sort of leave open doors for, okay, now you can try things out yourself. They're not in many ways special. They're just sort of a nice guidebook towards compression. And so I'm just going to give a very brief overview to them as they're being developed continuously, and have sort of the long-term view of serving as an entry point and a playground for compression. So of course, there are some notebooks that just showcase how do you compress data, some that showcase what type of compression methods are available and the errors they produce. Here on the right-hand side, we have a plot for sort of a very exaggerated error. And then, of course, we want to compare the compressors, see what compression ratio they offer, what errors they produce, but also, for instance, how expensive they are in terms of computation. The notebooks also deal with different types of data. So inside of ESiWACE, we've collected a few example data sets that showcase, for instance, the different data formats, the different simulations they come from, how you can easily load them and then analyze them, compress them, etc. Again, to provide a good entry point for somebody to go, okay, I have my own data. It's a bit similar to this. Now I know how to start using it and compress it. And then the last part, which is the part we're still mostly working on, is case studies. So taking some existing variables and really digging in what would be the best way to compress it at the moment. Some case studies we're working on is one for precipitation, and then one for not compressing model outputs, but actually model states while the model runs as sort of really stress test of what actually happens if you apply lossy compression to the inner workings of a model. Are you breaking anything, or is there a way to do that safely? And over time, we plan to expand those case studies to again give sort of an entry point of here is a pipeline for how you can find which compression works well for you. And a larger scale, but less detailed way of doing this will also be the benchmarking that we're doing. Now, of course, I can talk a lot and show some slides, but let's actually show it in practice. So here, and I hope this is now nicely visible, here I'm actually already now in the online laboratory showing a demonstration notebook that is very similar to the ones we have in the compression laboratory. So far, all I've done is I've downloaded an ETSDF dataset, and I'm now going to use X-Array to open that dataset. And here we have it. It's just the 2-meter temperature. And we can use ECMWF's EarthKit library to plot that data, to sort of get an overview of what the data is looking like. And there we have that. Then for demonstration purposes, we want to apply some very bad compressions so we can actually see what can go wrong. So compression is quite simple. We just define a list of compressors we want to use. In this case, we use bit rounding, which just zeroes out some mantissa bits and a floating point number. And we only keep 5 of those mantissa bits around, so we expect the compression to be very bad. And then we again plot the results of that. And here you can see sort of what bad compression might look like. Of course, we also want to know about what the compression actually did. So the online laboratory provides ways to sort of monitor how it went. In this case, we are showing the compression ratio. Bit rounding actually by itself doesn't compress, just makes data easier to compress. And so here we achieved with some very simple ZNet compression a factor of about 75. And we can also see how many instructions it took to do the compression as a sort of proxy for computational load. We can see bit rounding is quite cheap, but ZLab is a bit more expensive. And then finally, of course, what we always want to do is look at the errors. So here we're going to subtract the original data from the compressed data and plot it. And as we expect for a very coarse and bad compressor, there's going to be quite high errors. And especially there's going to be patterns, which is what we don't want. If there are patterns in the error, it means we've lost something. But for demonstration purposes, this can sort of show how easy it is to try out compression yourself on some data. So now that I've given a sort of very brief overview of the notebooks we're providing to explore data compression, I now want to make the step of where we don't just provide notebooks, but where we provide an entire online laboratory to explore them, and not just data compression, but climate science and meteorology more generally. So of course, this asks the question, why are we doing this? Why are we doing more work here? And this goes back to our motivation. We want to convince domain scientists that lossy compression can be applied safely. But a big important part of that is I cannot convince anyone. People need to be able to convince themselves. Somebody can always do some data analysis, but that's not going to be as convincing as trying things out yourself on your own data and seeing that things work and are safe. So we need to allow people to convince themselves. To convince themselves, it's really important that you can try things out yourself. So use your own data, use your own analyses, and see the impact that compression has, and verify that it is safe to use. But of course, oftentimes when we have a computational example and we say, okay, try this out yourself. There's a lot of setup cost involved. You might need to create a new Python virtual environment. You might need to install some software. Maybe those Python packages have some binary dependencies. Then you need to hunt those down. And at the end, you've lost minutes, if not an hour. You're very angry at having to do all of this. And of course, it means that nobody tries things out if it means you have a potentially high amount of time investment just to get started. So because we want to allow people to try things out, to convince themselves, we need to really reduce this initial setup cost. We want to allow people to say, okay, lossy compression is an interesting topic. I want to see for myself, and I want to see it now. And so how do we do that to allow more people to engage with our work? Well, trying out lossy compression should be easy. And so let's make it as easy as possible, which is just open a website. In slightly more technical terms, we are running essentially a container that contains a locked Python environment, but instead of running it anywhere on a server, it runs just inside your web browser locally using WebAssembly. And so to try out compression, you can go to the compression.lab.climate.eu link or this QR code, and you'll be greeted by this. So now we are in the online compression laboratory, where I just showed you an overview of that earlier. So there's some introductory README, and then here on the side, we can see all of the notebooks that I showed screenshots of earlier. So notebooks that introduce data compression, that show how to load different data examples, etc. And the most important thing is once you load the website, it takes less than 1 minute for all of this to be there. And then you can just get started immediately, and you have a running Python environment with all the dependencies that you need pre-installed. So it's very quick to get started and to try things out yourself. So to summarize again, we really want to make it as easy and as quick as possible to just pick things up and go and try things out. And what could be easier than just opening a website? Our goal is to make it as easy as documentation. So we're probably all used to, for instance, Python being able to read the docs documentation. So it should be just as easy to just click a link and there you can see it. But often documentation is very static. You can see that, for instance, a library produces nice plots, but you want to try it out yourself. So we want it as easy as documentation, but interactive. Of course, because we're now running Python not natively, but inside this WebAssembly container, it's going to be a bit slower. But this is sufficient if you just want to try things out, if you want to bring an example closer to the people, to your stakeholders who want to use it. And so the goal really is to push the setup cost as late as possible, essentially to first invest people in really wanting to use something, in our case, lossy compression, convince themselves that it would be valuable to them. And then once they're convinced, then they can go install a Python package natively, install some native software, and then use it in production. But it's really about making those first steps to just exploring something, finding out something new, being curious as easy as possible. I'm going to give a very brief overview of how the online laboratory works. So, of course, normally if you want to run a Jupyter notebook or JupyterLab, you have the local or hosted somewhere else server stack. So you're running Python on a server and then Jupyter as well. But this, of course, costs something for the one running the survey. It's either you running it locally or somebody else. And again, we want this to be available to as many people as possible, and we don't want to host those resources. So let's instead scrap that server and do everything locally in your own web browser. So a way to think about it is it's a serverless container, Python inside the web browser, and there are some existing community projects that we build on. So instead of Python or usually C Python running locally, we use Pyodite, which is C Python running inside WebAssembly. And instead of Jupyter, we use JupyterLite, which is also just a Jupyter distribution running in the web browser. Importantly, our goal here is that you can always use the same code with the same interfaces to get the same results, but without having to install anything. And that, of course, makes it very easy to also share some code. Because again, the other person doesn't need to set something up. You don't have to worry about them having different dependency versions installed. You can just share your code and it will run in the same environment that you're running it in as well. Now, thankfully, we're also able to benefit from a shared community ecosystem of making Python run in the web browser. So there are, for instance, pure Python packages, which just work out of the box. Then for the really important core scientific packages, the PyDite project has already ported them to work inside this WebAssembly distribution, and we've contributed to that as well. And then sort of the last side is the main specific side for Earth science and climate and meteorology, where a lot of those packages had not yet been ported, and so we've now ported them. So important packages like EC-codes, NetCDF, Car2Buy, etc. Are able to be used inside the online laboratory without needing to worry about how they're being used. You can just use the same code as always. Another focus we have in the online laboratory that's a bit more specific than the projects we're building on is really reducing user friction, in particular to working with big data, because again, we want to explore data compression, and so we want to work with big data. In climate, of course, the first big thing is which format you're loading your data in. The big ones are ZAR, NetCDF, and GRIB. ZAR is the easiest one to work with large data because it already supports streaming. It's natively chunked. And ZAR doesn't really care where your data lives since it builds on FSpec. So anything you can duck type to look like a file system can store ZAR data sets, and then you can load them. And because it's chunked, even if you're working inside a web browser where you have really little memory, you can always work with big data because it's just streamed in as you need it to. NetCDF sort of slightly more difficult to support. It's also chunked. It has some separate metadata, but it, as it's an older format, doesn't support as many backends. But thankfully, there's a nice way using the CurveChunk Python library where you can sort of make a NetCDF dataset look like ZAR. So data still is stored in the exact same location. You don't move it, but you add a bit of metadata on top, and then you can use ZAR as normal to load the existing NetCDF data. You can do a similar thing for GRIB, but because GRIB doesn't have this metadata, you need to do some pre-processing. And so, for instance, for those example datasets that we provide with the online compression laboratory, we've done this pre-processing. So again, you can load GRIB files of any size, even in this very memory-constrained tiny online laboratory. With smaller datasets, of course, all of this doesn't matter. You can just download them using any library you like and use, for instance, from the Climate Data Store or using the new EarthKit data package, and then they're just loaded via the native drivers. Another feature that we have is if you already have the data stored locally or on a disk that's you can access locally, you can just mount it into the online laboratory without needing to ever copy the data, and then you can just access it at native speeds. And with all of those, we sort of again try to make it as easy as possible to use your existing data analysis code inside the online laboratory to just get things running very quickly and conveniently. So far, of course, I've talked a lot about the particular use case we have for having this online laboratory, which is data compression and making this as accessible as possible to others. But at some point, we asked ourselves the question, well, this is useful to us. Could it be useful for other ones as well? And so we started moving the project also more into the community collaboration and providing a service to the greater community direction. Because what we provide is really useful. We provide a block Python environment with pre-installed packages. So it's very easy to get going and know that things will run correctly set up. Importantly, because the JupyterLab environment is running inside your web browser and locally, it means neither notebooks nor data ever leave your computer. So for instance, if you're working with sensitive data, you don't have to worry about sending that data to some server running elsewhere. It's completely compartmentalized. And all of that already allows, gives sort of the first service to the community, which is being able to share your existing notebooks quite easily and allow them to run. And so, for instance, in the online laboratory, we support a very easy URL schema where you, for instance, can just fill in the name of your GitHub repository. And when that URL is opened, it will pull in that repository and you'll be able to get going immediately. And actually, that's exactly the way that the online compression laboratory works. It's just a GitHub repository with Jupyter notebooks, and then we just run that in the compression laboratory like any other project could. Another thing you can do, and this goes back to wanting the online laboratory to be like documentation but interactive, is to actually make existing documentation interactive. So here I've taken an example from the EarthKit plots documentation, which right now is static. There's the read the docs link at the bottom, and it hosts a few Jupyter notebooks. And as you can see from the links at the bottom, it's very easy to transform one link to the other. And then again, when you click that link, it will automatically download that notebook, and you're ready to go within less than a minute. And you can no longer just look at the example and say, oh, that's very nice. But you can run it, you can change things, and you can see how, for instance, this might be useful for yourself. And with this, I will sort of transition to giving a future outlook, what we're working on currently, both for the laboratory, but also on the compression side. So for the online laboratory, we're really working towards this community service direction. What I've already mentioned is you can already open your existing repositories or notebooks hosted anywhere online in the online laboratory, and therefore make it a lot easier to share them, to allow other people to get started and try things out immediately. What we're working on at the moment is to make it also possible to customize the Python environment that it runs in. So far, it was always very specific to the compression laboratory, but of course, a different project might have slightly different package requirements. And so we're working on making it possible to just supply essentially a requirements.txt file, but slightly different format. And then again, still your end users will be able to just click a link and it will automatically have all the packages there and ready to go. And the goal sort of mid-late 25 is to really allow anyone to produce, share, and try out repositories, interactive documentation examples, and we're planning to use them in our own scientific publications so that instead of just having a static example, we can have a link and people can immediately try things out. On the roadmap to fearless lossy compression side, what we're working on at the moment is the first point I mentioned earlier, which is establishing the clear safety requirements we have. So how can lossy compression be safe? And we're also working on benchmarking existing compressors to see which ones are safe and how performant they are. What we will work towards next year is these safeguards I mentioned, so that you can always take any lossy compressor, no matter how bad or unsafe it is internally, and wrap it up so it is very safe to use. And that will make it a lot easier for the main users. Just pick the latest fancy looking compressor, try it out, and you will know that it is safe to use no matter what. And so the end goal of ESiWACE3 towards data compression is to then really provide recommendations for how you can use lossy compression operationally in a safe way. And sandwiched in the middle and supporting both of these is really our community outreach, supported and facilitated by the online laboratory. So because a lot of our work is presenting our findings to the community, allowing them to convince themselves, we've built this quite nice tool. So you can very easily try things out yourself. And now we also hope that it can be used by other projects as well. So we can provide it as a larger service to the weather and climate community and just foster more sharing and more collaboration in general. And with that, I've done. Thank you very much for being here. Of course, there is an even bigger list of people who've helped with this project, so I wanted to acknowledge those. And if you want to get in touch with us, probably the easiest way is via the GitHub organization or GitHub repo, where we're developing the online lab and the compression laboratory.
Thanks a lot, Juniper, for this very lively and interesting talk with a lot of fresh ideas. And the floor is open to everybody's questions. Okay, but I think this was then the last question I see. So thank you again. And we will have a next meeting in about 1 month on a bit different topic.
Indeed, thank you again for the talk. Have a good day. Bye.
Bye.
Thank you. Bye.